All right, Mr. Rainsberg here. We are looking at lesson 5.2, and these are really the rules of probability. So this is it's only two targets that we're trying to hit here, describing chance behavior with the probability model, but there's a lot of things in what is a probability model and what creates it. And even just the basic rules of probability, we're told they're basic rules, but don't let that word basic fool you. It's really got a lot of meat on what the rules of probability are. So we're just going to cover those two in this video, and the next video will cover the two-way tables and the Venn diagrams because those relate more to each other. So when we look at this, probability models, these are perfect scenarios. It's not reality. And think of it this way, if you were to flip a coin 8 times, are you always going to end with 4 heads and 4 tails? And no. But in the perfect scenario, in the probability model, it would come out to show us all the possible outcomes. So probability models are the perfect scenario, what would happen in that case. They're not reality for it. And we have a sample space. And so when we look at a probability model, we are trying to create what are all the outcomes, all the possible outcomes, and let us determine the probability of them. So we can list out the sample space, and we use a capital S for that one. And it gives us the chance process of those outcomes. And then we have a probability model. It's a description of that process. And that probability model comes with the sample space, which is the set of all possible outcomes, and it comes with the probability of each outcome. And so we have this right here. We have 2 scenarios. We're asked to list the sample space of rolling a die. Now I can go get a die and I can roll it like Mr. Nichols did in that video a few times. But what is the sample space when we roll a die? Well, you have 6 outcomes. You can roll a 1, a 2, a 3, a 4, a 5, or a 6. Unless you're playing Dungeons & Dragons, then you can do a 10 on it. But we're doing a 6-sided die. Let's not go there. And so there's our answer. We have S equals, and we use the braces to represent the set of outcomes. And so 1, 2, etc. There's our 6 possible outcomes. Now, if I wanted to do a probability model of this, and on top of writing this down, I would also write down what's the probability of rolling a 1. And so the probability, should change the size of this, the probability of a 1 is 1/6. What's the probability of a 2? Well, that's 1/6. Probability of 3, etc. I would list out all those probabilities. The next problem says, hey, list the sample space for flipping 2 coins. So if I flip 2 coins, I can get a heads and a heads. I can get a heads and a tails. I can get a tails and heads, or 2 tails. And so that's what I would list out for it. Heads, heads, tails, 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 tails. And you could figure out the probability for those if you wanted a probability model. So a sample space just lists out all the possible outcomes of them. And we can go a little bit further with this. Is what if I rolled 2 die? Now this one's not completely in your notes packet. The next slide we're going to kind of look at more, but this one is just showing you. If I roll 2 die, here's the sample space. It's not the probability model of it because all I'm doing is showing you the 36 possible outcomes of this. And so you see the orange die and the green die and all the outcomes for it. Each outcome, since it's a fair die, has a 1 out of 36 chance of occurring. There's 36 possibilities listed out there. It says red and green, but I see it as orange. And so when we look at this, we can see all the outcomes. And that's a lot of writing to do that. It takes up a lot of space to write out all these outcomes. I wonder if there's going to be a way for us to discover to do it faster on it. So this one shows us the event occurring of rolling 2 die and getting the outcomes of it. Now, if we want to do a legitimate probability model, remember, probability model lists out the probabilities involved in each one. You can see I have these blank spaces for you here. That's going to create a probability model. Now, this definition might not seem important to you, but it really is. It seems so basic, but trust me on this one. This right here on what determines a legitimate probability model is extremely important. You think it sounds basic, but it's something to always keep in the back of your mind. A legitimate probability model they have to have values between 0 and 1 because that's probability. Probability has either no % chance or 100% chance on it. So it's between 0 and 1 is where the outcomes are. You can't have a 120% chance of something occurring or a negative % chance of something occurring. So that's really important, as your outcomes have to fit into the definition of what creates a probability as a decimal between 0 and 1. It also means all outcomes in the sample space must add to 1. So the outcomes of the probability model must add to 1. It's something that students, but people keep forgetting to check. So always when you have a probability model, make sure if you're creating a probability model, make sure your probability model adds to 1 for them. And so we have this right here. Here's all of our outcomes. We're looking at the sum of rolling 2 die. And we want to know, hey, what's the probability of having a sum of 2 from rolling 2 die, or a sum of 3, a sum of 7, of 9? And so a sum of 2, I'm focusing, and I'll use blue, right here is the only outcome for it. That's 1 out of 36. And I'll just write that right here, is, probability of a sum of 2 is 1 out of 36. What if I wanted the sum of 3, the next one? I'll change my highlighting color. Is right here, 1 plus 2 is 3, and I could do 2 plus 1. And so in this case, the probability of a 3 is 2 out of 36. And let's see what happens. We'll go to red to prove to you that it is an orange die, not a red die. Is here's, yep, I can see it. And so here's a sum of 4. So if you're doing this and you see this right now, you should be able to notice it looks like I'm hitting these diagonals from it. And so I'm just going to fill in the rest. If I go through and do this, then the sum of 5, if I count, and I'll use the mouse for this, is 1, 2, 3, 4. I have 4 out of the 36. A sum of 6, 1, 2, 3, 4, 5 out of 36. And notice I'm not simplifying. And again, that's because we're dealing with a probability model. So what I'm going to do is I'm going to cheat. And I'm going to take, and I actually had them written down already, these numbers, and I'm going to slide them in the right spots for it. And so here are the answers. Boom. And we can go through and see this big diagonal right here has a sum of 7. And there are 6 of them there. And then it starts going back down. A sum of 8 would be 5 out of 36. 9, 4 out of 36. And the reason why, while you're writing these down, you can kind of listen, is the reason why I did not simplify is because it's going to be much easier to check, is this a legitimate probability model? If I do 1 plus 2 plus 3 plus 4 plus ... and count down, does it add up to 36 out of 36? Does it add up to 1? And it does. So the reason why I'm leaving these denominators, and don't try and simplify it, leave them like this, there's no harm in it here, is they have to add to 1. And by keeping a common denominator there, it's easier for us to do that. And so there's a very basic idea. The top part right here is our sample space. This bottom part right here, that's our probability model on it. It's listing out all those probabilities for us. So now, we can go a little bit further. Probability models, they allow us to calculate probabilities. So right here, you go, well, why is that helpful? Because I could ask you a question now. I could say, what's the probability of rolling a 9 or higher? Well, here's a 9, here's or higher. You could add those. You could give me the probability. I could ask you, what's the probability of rolling a multiple of 3? Well, 3, 6, 9, 12. I could add those and get it. So that's how probability models are helpful for us. It allows us to calculate probabilities of a certain scenario. So an event is any collection of outcomes from some chance process. And so what we're going to do is we're going to look at calculating some of these. So we're going to first, and I kind of pay attention, this is stuff, again, I always like to point out things that are in the notes that you kind of skim over as a student, but you need to pay attention to it, is right here, that if A is any event, we write it as probability of A. The reason why that is important is you have to define your variables. and go back to chapter 3 with linear regression, is if you used y hat, you had to say y hat equals the predicted value of this. And it's the same here. If we're defining an event as A, you really better define what is A in context of the problem. You can't just write down A. You know, suppose you define event A as a sum of 5. So it's defining it. You always define the variables that you're going to use. Then you get to use it. If you don't define it, you don't get to use it. So that really means the probability of a sum of 5. Well, from our situation, if we come back here and we look, I mean, I could go and look at my sample space if I wanted to, but you know what? I'm just going to look at my probability model. I mean, that's why we created it. So what's the probability of a sum of 5? Well, it's right here. A probability of a sum of 5 is 4 out of 36. There are 4 outcomes out of the 36 total that we need to do. There are 4 ones that add up to a sum of 5. Now suppose event B, again, things that students don't quite realize is we're defining it for you. But it's your job to define it on your own, on your homework and on the tests. So again, it's defining the variable. If you don't define it, you don't get to use it. So a sum that is greater than 10, the question is, does that include 10? No, greater than 10 would be 11 or 12. And so I'm going to look at, let's get rid of this, I'm going to look at right here. Greater than 10 would be these two. So that's 2 out of 36 and 1 out of 36. So technically, I'm going to write this down, greater than 10 would be the probability of a sum of 11 plus the probability of a sum of 12. That's really what I'm doing. And that would be 2 out of 36 plus 1 out of 36. That's going to give me 3 out of 36. Not going to simplify. You just go ahead and leave it alone. Number 3 is going through, okay, find the probability of AC. Now, we don't call it AC. It's called A complement. And this is something that's not there on your notes, and you need to kind of make sure you write it down. It's also a definition we're going to cover a little bit later on. But what the complement is in a way, the opposite of it. The opposite of the event occurring. So, find the opposite of the event occurring. Well, I could, and this is where it becomes tedious, the opposite of event A. So I want the sum, the probability of a sum of not 5, and that's really what this is asking, is I want the probability of a sum not equal to 5. And that's really what we're going for here. Well, I could take and add every single one except 5. But that's tedious, and that's annoying, because I have to add 11, in his case, 136, 236, 336, 536. No, that's way too much for me. I'm not going to do that. So I need to figure out a better way. And the better way of doing it is with the complement. If you have a legitimate probability model, it adds up to 1. And that's where this picture is kind of here to show you. That entire box is 1. Has an area of 1 inside of it. And so the event A occurring, and this would be the sum of 5. So we'll have here the probability of a sum of 5. The probability of not 5 is that green space on it. This part. That would be the probability of a sum of 2, of 3, of 4, of 6, of 7, of 8, of 9, 10, 11, 12. That's what that green space represents. So instead of adding up all those numbers, what I can do is realize I can take the whole probability of 1 and just subtract the white space. Subtract the sum of 5. If I do that, that would give me the probability of just the complement itself. That's what the complement is. It's the opposite of it occurring. So if I do the complement of A, the probability of a sum of not 5, I can do 1 minus the probability of a 5. And in this case, I get probability of A complement is 32 out of 36. That's it. It's one of those things where you need to be aware. We're going to discuss more about complement, and this just kind of introduces the idea. So we have our answers for it right here as well. Quick change of screens there. So now let's go through this. I said we talk more about the rules of probability, the basic rules of probability. They're not basic. What we need to do is we need to kind of discuss complement a little bit more. And we're going to, again, talk about more at the end. But what the complement is the probability of the outcomes that are not in A. So A complement are outcomes that are not in A. And you can see that with that diagram. You have the white circle and you have the green outside part for the whole event 1, the whole square. And so the green space is not in the white space. And so therefore that's our complement of A, the outcomes that are not in it. And this just tells us how we write it and how we say it. If you want a complement, you put a superscript of C up there. And if it's read as the probability of A complement, not the probability of AC. It's probability of A complement on it. And so let's, that was just to kind of refresh our memory a little bit from the previous problem, this stuff down here. But it's something to keep in mind. It's new for you. The next part that we're going to do is we're going to look at legitimate probability models. Well, why? Because I told you, it's extremely important. It's things that students tend to forget. Those two rules seem so basic, but they're really still important to do. So, a legitimate probability model has to have values between 0 and 1. And they must add to 1. It has to be both of those on it. So in the first case, right here, this table, it's blue. Remember, blue side's not in your notes packet, so now all attention's on me. And so when you're going through this, we first want to check. Do they add to 1? So if I do 0.2 plus 0.1 plus 0.3 plus 0.1 plus 0.2 plus 0.2, does it add to 1? I also want to make sure all those probabilities between 0 and 1. So if I do the latter one first, all those probabilities are between 0 and 1. So that is checked off. Do they add to 1? Well, if I do the mental math first, I think this adds to 1.1. So I look at it. This is not a legitimate probability model. You can't just say no, you have to explain why. And the reason why is they do not add up to 1. Now if I look at the second one, let me try the adding first. If I take 0.1 plus 0.3 plus 0.2, and plus that negative 0.1 plus 0.3 plus 0.2, it does add up to 1. So I can't use that same answer. But did you hear what I said at that fourth one? I said plus negative 0.1. Probabilities have to be between 0 and 1, and they have to add to exactly 1. They have to fit both those criteria. This one does not fit the between 0 and 1. It has a negative probability with that number 4 outcome for it. The last one, let's see, in this case, if I add them, I get 5, they do add up to 1, check, and they're all between 0 and 1. I think this last one is a legitimate probability model. I'm going to say yes, but not just end with yes. I'm going to tell you why. Because each outcome is between 0 and 1, and the sum of the outcomes is 1. It fits both criteria. So let's look at the different counting methods. And I'm talking about this, it is kind of, you might think it's jumping around, and I'll transition it for you. Do you really want to draw out this sample space to determine that there are 36 possible outcomes? Unless you're bored. If you're bored, go to town, have fun with it. But to do that on a test would take a lot of time. So what we use is we use these counting methods to help us out. We could create a list, an organized list, and that's what we did before, a diagram for the 36 possible outcomes. Nothing wrong with that. Unless you have a lot of outcomes. Then that takes way too much time. And it's the same with the tree diagram. The flipping 2 coins problem, I could say, again, need to change the size. I could say the first coin is a head, the second coin is a tails. Okay, well if I flip another coin, heads, tails. That's not bad to do a tree diagram for, because I can see my outcomes. Heads, 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 tails, tails, heads, tails, tails. Even if I do another one on here, heads, tails, heads, tails. Now it's not that bad. It's starting to get a little annoying. What if I do a fourth coin? Now I don't want to, because that's going to take a lot of drawing for it. So tree diagrams are great when you have a certain, I'd say in my mind, a certain amount of events occurring for it. a great way to do it, and the way you start to go into, is this multiplication counting principle. You might have heard it called before the fundamental counting principle. And that tells you if you have n number of ways of doing one task and another number of ways of doing another task, just multiply them together. So instead of doing a diagram or organized list or a tree diagram, I'm going to use the fundamental counting principle, the multiplication counting principle, to answer these two questions. If I have 3 pants and 4 shirts, to find the total number of outcomes, I'm just going to multiply them together. There should be 12. And by the way, there's proof of this. There are, if I'm flipping 3 coins, I have 2 outcomes in the first coin, I have 2 outcomes in the second coin, heads or tails, and I have 2 outcomes on the third coin, heads or tails. 2 times 2 times 2 is 8. See, 2, 4, 6, well, yep, there were 8 possible outcomes if I followed the tree diagram paths on it. So the fundamental counting principle, the multiplication counting principle, allows us to skip to find the total number of outcomes. So if you go to Chipotle and you want to consider the form, you got a burrito bowl, you have a burrito, you have a salad now, you have, by the way, you have brown rice, you have white rice, you have all the different beans, pinto beans, black beans, fajita, meat, the salt, so many different outcomes on it. So if you want to figure out the number of meals, you know what, have fun with that one. It's a pretty large number. But it's meant to show you the more events that you have, the less likely you're going to use these, and the more likely you should rely on the counting principle to help you out. So let's try this example. Distance learning courses are rapidly gaining popularity among college students, I would say across all students. Randomly select an undergraduate student who is taking distance learning courses for credit and record the student's age. Here's a probability model. Bam. All right, so show this as a legitimate probability model. So notice there's 2 things you have to check. Each probability is between 0 and 1. 0.57, 0.17, 0.14, 0.12, between 0 and 1. And if I add them together, it is going to equal 1. So it is a legitimate probability model. The next part is saying find the probability that a chosen student is not in the traditional college age group. The traditional college age group being between 18 to 23. Well, we could. If it's not in that age group, I don't want this. I want the others. So I could just add them all together. And that's what most students would do. But what if you didn't know these? So let's go back to making it big. What if I didn't know these? What if I knew the ages, but I didn't know the probability? You couldn't do that then. So just because you can do something doesn't mean you get to do it. Sometimes there's a skill behind it that you need to be aware of. I could, if I know only that, I could find the probability of not the traditional college age group by doing our complement rule. And that's the point of this example, is yes, you could add them together like we have there, but it's meant to make you realize, what if I didn't know those numbers? Well, I'm going to have to do my complement rule. So I'm going to do 1 minus the probability of that event actually occurring, because they should add up to 1. That was what we learned in Part A. So if I do 1 minus 0.57, I will get 0.43 as well. So again, I know you could have, and I said at the beginning, you could have done this. But if you did not know this stuff, you would still be able to find the probability of not traditional by doing the complement rule for it. So here's the basic rules of probability that we've discussed before, and it looks like it's a lot, but you realize we've covered these. For example, if you look at the first one, for any event A, the probability of A is between 0 and 1. That, plus the second bullet point, the sample space in a probability model, is equal to 1. These are the two, gotta again make it thin, need to keep track of this. This is our definition of a legitimate probability model. So we've already discussed these. In the case of equally likely outcomes, the probability of event A is the number of outcomes of that event divided by the total. Well, we've used that when we did the die problem. Probability of a 5. Well, we counted how many times the sum of 5 occurred divided by the 36. So that's really what this is telling you. So we've covered that already. The complement rule, we've talked about that. We've discussed it. We analyzed what this was. We determined what it was. We did an example of it. I try to show you the point of why it's important to use it as well. So that's the complement rule. So we've covered everything up above here. Now there's two things. There's a mutually exclusive event. You might see it as the word disjoint. And that means they have no outcomes in common. So the probability of event A or B occurring is the sum of them. And so we have that's mutually exclusive. So two events not occurring. They have no outcomes overlapping. If they are inclusive events, they have an overlapping. So exclusive, no overlapping, inclusive, overlapping. And the general idea is it gives you this general addition rule for probability. Is I always focus on this one. If you have an event A and B, to find the probability of one or the other occurring, you add them. They both agree with this, you add them. What's the difference? What if there's overlapping? What if they have a common outcome? Well, then you need to subtract that common outcome once for however many times it occurs. I say once for however many times it occurs. That's what this is. This is the overlapping. Because you counted it twice. You counted it in event A, you counted it in event B, so you need to subtract it because one time because you counted it twice. And so that's something to keep in mind, is you always add them together. You always look for the sum of two events occurring. If they're mutually exclusive, well, you're subtracting 0 because there's no overlapping. If they're inclusive, you're needing to subtract what it is. And so that's where these two definitions come in. Mutually exclusive disjoint have no outcomes in common and they're never going to occur together. Mutually inclusive, which is referred to as not mutually exclusive. They have outcomes in common and they can occur together. So what are some of these before we move on? Well, let's talk about the bottom one, the not mutually exclusive. If I have a deck of cards, what's the probability of randomly drawing an ace or a spade? So I'm okay with the 2 spades, 3 spades, 7 spades, 8 spades, 9 spades. I'm okay with an ace of spades, a ace of hearts, an ace of diamonds, or an ace of clubs. But if you think about it, there's overlapping there. You have the ace of spades. I counted that twice because this was counted in the spades group and it was counted in the ace group. So I would have to subtract however many times it overlaps, and it overlaps one time. And that's a not mutually exclusive example for it. I mean, what were the odds of me drawing the ace of spades there, right? No one ever stacked the deck before. Now, not mutually exclusive would be, what's the probability of, and I really hope this works, drawing a spade or a heart? Well, a heart can't be a spade can't be a heart. There is no overlapping between those. That's mutually exclusive. Is there are no outcomes of hearts that are also spades. That worked out so well. And so, let's try one out. And we look at this is the last example of the video. You almost made it. Here's what we're going to do. And I want to talk again just about some of the things that are important as a student. Is we have defining the variables. So in this case, it's really, really important that you understand, yes, it's done for you, but your job is going to be to define these variables. And so it's telling us, hey, choose an American doll at random, we're going to have 2 events. Event A is this person has high cholesterol, which is defined as 240 or above. Or this person has borderline high cholesterol, which is 200 to 239. If the probability of event A, so now that they defined it, they get to use it. Now that they defined it, they get to use it. So the probability of someone having 240 or above is 0.16. Someone having blood pressure of 200 to 239 is 0.29. Are these events mutually exclusive? So can somebody have blood pressure that is 240 and above at the same time have blood pressure between 200 and 239? And the answer in that case is no. A person cannot have both high cholesterol and borderline high cholesterol at the same time. They can have cholesterol level 240 and above. Pick a number, 270. So is 270 also between 200 and 239? No. You can't have both. You're either in that borderline or you're high. You're not in both. So these two events are mutually exclusive. There's no outcomes that overlap on it. Number two, like I can see it up here now, is say in plain language what the event A or B is, and then find it. So it defined it for us. Event A is someone has high cholesterol, 240 or above. B is someone has borderline cholesterol, 200, 239. So if I want to say it in plain language, I'm going to say a person has either high cholesterol or borderline high cholesterol. Since there's no overlapping, since they're mutually exclusive, I just add my two probabilities together, which were given to us. They were 0.16 and 0.29. If you add those together, you get your 0.45. And I can do that and not worry about the overlapping because of this right here. I knew they're mutually exclusive. So when you're thinking and doing probability, you need to ask yourself, do they have any outcome in common? If they do, subtract the overlapping. If they don't, pretty simple. Now, number 3 says if C is the event that a person chosen has normal cholesterol below 200, what's the probability of event C? In other words, what's the complement of A or B? And you have to realize in this scenario, they only gave you high blood pressure and borderline high blood pressure. They never told you normal or low blood pressure in that case. But we can use our complement rule to help us. I could do 1 minus the 0.45, and that will give me the complement of it. So this is just a very basic check your understanding. You should be able to do the two parts at this point for us. The next video goes into two-way tables and goes into Venn diagrams.